There is another handout which I provided. It's on Blackboard. This is just summarizing everything we did so far. So, for example, we did tailored series and just giving you one sentence on what that entails. So, estimating the value of function in the vicinity of a given value. So, if you want sine 0. You would estimate 0.5 plus 0.0001, then you can use this estimate using a Taylor series, and so on. So I just put everything here. And the reason I put it there because given a problem, you need to be able to figure first out what tool or technique you need to use, or rather which section it belongs to. Without that, you cannot apply a particular technique. So that's why I summarized everything over here. Okay, so that's one thing. I created a few questions here. We may not be able to finish all of them. We'll just carry them forward to the next week. But few classes, I'm not thinking more than next week to go through this. So hopefully next week I'll be done with this part too. Okay, so another thing I did was I took all the I took these files. These are like zip files which I provided to you at different times in the semester. So for example, for roots of equations, I provided these files. So for example, if you want to run bisection, Newton-Raphson, regular falsy, you just run the main root, and then you'll be able to run that, right? So all these are downloaded from Blackboard. Okay, and what I'll do today is I'll basically use mixture of them and search on the web to solve these problems. Okay, and hopefully this will also show you how I code. So just like you, I'm not a trained computer scientist or computer engineer, and so I just learned this by myself. So maybe some things you can take from me, some things you have a different way of doing things, but I hope that it's helpful. Okay, let me just do one more thing and we'll get started. Okay, so numerically compute the integral below and compare against the exact value. So here we have 1 divided by e raised to x plus e raised to minus x, and then limit goes from 0 all the way to infinity. Okay, so if you think of integration, you could go to this 2-page handout and see how to do numerical integration. You can integrate it with some of these methods. Okay, and you could also use Richardson, Romberg, but then that really requires you to use rectangular trapezoid or one of those methods. So instead of trying to do it, we'll not use this clearly. We'll just stick with one of these. Okay, so we can then go to my codes. I have integration code here. So rectangular Simpson, and I think if you take this main integration and all these files, okay, so I'll take those files and let's make a folder. So let's go to project and let's say November 3rd, today's date. Say Q1. It's always easy to start from something which is already existing versus staring at a blank screen. So here, let's open this file. So I already opened Octave. This is integrating what? X square, x cube. You can see if this runs fine. It produces solutions using rectangular two ways, trapezoidal Simpson. Now, I know the rectangle rule is not very accurate, so let me just get rid of that. I comment that out. Okay, so let's start modifying this file, right? I need the exact integral, and I need, so let's read this here. So exponential x plus e raised to minus x. So let's change this here. Okay. And there's so many things going on here. Let me just use one of these rules and then I can just generalize it to others. So let me get rid of these. I'm not interested in exact right now. Let me just get this thing to work. Okay. And then I need to choose n. I can choose, well, the limits are 0 and infinity. Okay. And infinity is really hard to represent using uh, the computer. You just can't put infinity, it'll crash. So I probably can only integrate it to some big number, but not infinity. That's one of the issues with numerical methods, right? So why don't I just move this to, let's try 100 first, and then we increase it. And I know that for 100, maybe 6 is a bad number. Let's try 100. And let's say go. Okay, so there's a problem. Error for x raised to only square matrix arguments are permitted. Use dot raised to for element wise. So it's telling me that the error is in line 5. So main integration trapezoidal line 4 and this line 5 seems like it's coming from the anonymous function. So the error is right here. Okay. And I suspect that it is because of this, which is saying that it's trying to create an array. And when you create an array, this is somehow not compatible. So we can check this actually if this reasoning is correct. So if you take what the trapezoidal rule will do is it basically create an array, let's say, just to check 0.4, right? And then if you take this function, which by the way is already stored in memory, so if you type f, it sees that. So if you can just say f x, so you see that so the error is coming. I just took a simple example, x equals whatever those 3 numbers. So it's not able to multiply, create the right f when x is this. What I expect this to do is I needed to evaluate f of 0, f of 0.1, f of 0.4, and that's what's not happening. So I need to change this. So the hint is here, somehow raised to is not working well. So can you guess what might be wrong with this function? So that when I do f of x, I get f of 0, f of 0.1, f of 0.4. There's something wrong here.
Or after the e.
So this is saying that should be just before the.
Yeah.
So this. Okay, so here's how you check it. Just take it.
Then professor, don't forget to change your n. You have 100 line 12.
Thanks. Okay, so let's paste this. And f, okay. X is still there. F of x. Okay, so now it's complaining a different error. OP1 is 1 cross 1, OP2 is 1 cross 3. What does that mean? Okay, let's try something simple. How about 1 times e raised to x? So there's an error right there. So simplifying it. This it doesn't like. If you use 1 divided by e raised to x, it doesn't like. This is a different error. So somehow it looks like this doesn't work. Oh, that works. Okay, so that works fine. So when I do 1 divided by e raised to e dot raised to x, that doesn't work. Okay, what is the error? How can I get this to work to print the value of a value for each of those x's? Can you guess? What's e raised to x? That's an array, right? It's right here. What I'm doing is I'm doing 1 divided by array. Do you think that'll work? Right. So if you do this, that works. So it's this 1, you did do element wise multiplication. So it'll create 1, 1, 1, and then 1 divided by whatever e raised to x and so on. So that's where the problem was actually. Is this big enough for you to see? Yeah. Is the font? Okay. Okay, so that's where the error is. I think, well, we can check it, right? So we can go here, copy this, paste here, f of x. It works fine. Okay, so that's the error. Let's run this. Okay, that's it. We found an answer, 0.7856. Okay, now we could now take this and go with some of the other methods. Yeah.
You have the weird sign of the yeah, the little
This one, what does it mean? It's basically a handle. Instead of writing it as this is the same as function f equals, I don't know, fun x. It's the same thing. These are the equivalent. What it does is basically it lets me define it in one line. So this is saying that x is the input argument, and this is the return value. So this will work as well as that one. The good thing about this is that I can pass it as an input argument. But if it was this, you just cannot pass it as an input argument. It's a funny way of doing it. I was kind of very uncomfortable seeing this, but that's how MATLAB does, Octave does it. It's a nice way because you can then send it as an input. Yes.
Main integration or main integration from
Main integration. Okay, so we can now, I just change Simpson's rule. 7780 looks like there is some changes in a decimal place. I don't know if, but there's no clue, right? We don't know what the correct answer is. So how would you know? Do you know if you can integrate? Do you know analytical solution for this? Have you done this before? We can just search online. We can just do that. Hold on. So what I would do is I would just search online. Integral of exponential. I think it's really hard to get something which is 1 divided by, yeah, it's really hard. Okay, so are you aware that there's a symbolic package in Octave? So we can use the symbolic package. The way this works is, what I'm going to do is, I'm going to write it here. So you could do it this pkg load symbolic, and then x real. This is going to be, x is going to be a variable, which is symbolic, and I'm going to integrate that. And so if you want to test it again, if you want to test anything, all you do is, you know what, let us write some test code. I always like to put CLC and clear all. Okay. Let's say f is x, so it's called f symbolic is x squared. Okay. You search Octave symbolic integration, it actually tells you how you can do it. All it says int f and do the integral for you. So int f sim, you can save it. Yes, there's a question, I think. Pi divided by 4. Yeah, that's the right answer. We're getting to pi divided by 4 in just a bit. Okay, if you run this, you get x cubed divided by 3. That's the right answer. So this is, you can use it. So here's how I like to operate. If I want to figure out something different, I just create a new file or use the command window, figure it out. And then it's just a matter of copy pasting it and modifying it to suit our purpose. So if you go here, put it there and put e raised to x, 1 divided by e raised to x plus e raised to minus x. Okay, let's see what it does. Okay, here's the answer. You see a z there? That's basically a complex number. It's just giving you a complex solution. Okay, it's clearly the answer is not complex. Just the idiosyncrasy of using that. However, there's a way to figure this out. There is actually a cosine. If you do cosine hyperbolic in terms of E, so I knew this now. This is something I knew, that you could write cosine hyperbolics as e raised to x plus e raised to minus x. So what you have there, 1 divided by e raised to x plus e raised to minus x, is actually 2 times cosine of hyperbolic x, like this. So because I know that, I can write this as 2 times cosine of cosine hyperbolic x. And now I think it will give you something meaningful. There's an error. I forgot to close this bracket. Okay, so it printed the whole thing, but this is the answer. Okay, so that's that is basically what the integral is. And you can put the upper and lower limit, and you actually will get pi divided by 4 if you put the upper limit. But you could also do it using octave. So if you go to octave, it tells you if you want to integrate from a to b, this is the syntax. You give the lower limit and upper limit. So let's do that. The lower limit is 0, upper limit is infinity, but you can't put infinity. Let's put some really big number, 10,000. Okay. F val equals this. And then it'll say disp F val, or let me call that int F. I'll comment this whole thing. I really hate to comment the whole thing, so I just put something which is not defined. So it'll just quit there. And so I'm really not interested in seeing what happens after that. So I just put some random value. So it will actually crash the code after that. So what I mean by crash is that it will not run that. I don't care about this. I really don't want it to do the calculations, but here it is. This is the answer seeking. You see, it's really strange. It's tan hyperbolic of 5,000. It's because the answer which comes out, so you can check int f, is actually symbolic. This is a symbolic value. So if you want to convert it to a number, then you need to say double. Okay, now how did I find it? Clearly, when I did this first, I did not know, but then I searched online, how do you convert a symbolic value to a numeric value? That's what I found. So now if you run this, it's 0.7854. In fact, it doesn't quite give you the in terms of pi, but pi divided by 4 is 0.7854. So that is the answer you get. Okay. So now we know the exact value. So when we did this calculation using, so that's the exact value. Let's run this. So the exact is 7854. We got 7856 using trapezoidal, and we got 7780. So it looks like trapezoidal is more accurate here than the Simpson's 1/3 rule. I think it's because of B, which is only 100. So let's make it 10,000, and then just increase the number of points. So now we have 10,000 points and 10,000 for the upper limit, which is actually infinity, and then 10,000 points for n. Okay, that did not improve it much. I'm surprised. Okay, that gets better. So it basically gets better for a large number of sample points, because that because e raised to x goes to infinity. There's a problem. So you will usually not see this problem with a function whose integrand, which is the thing in f of x, doesn't go to infinity. So for some value of x, like e raised to x goes to infinity, and that's where the problem comes. And there's e raised to minus x, which is goes the other way, which is for small values it's defined, but very big value it goes to 0. When it goes to 0, 1 divided by 0 becomes infinity.
Is it 100,000?
I drew 100,000. Yeah. Okay, I'll share all this with you. Okay, so I'm not really interested in these rules, but you could potentially try them with other ones and see. Now, an interesting thing is to use chord. Do you know what chord does? Chord is if chord. So chord basically integrates from A to B with some tolerance. So if you put a tolerance of 1e negative 6 and A and B are defined, okay, what do you think will be the outcome? You think it'll give 0.7854? Probably an error. .17. It's just junk. That's not right. I don't know why it gave that. No, I have F here. What if you change the B to 100? Now it gives right answer. So it behaves weirdly when B goes to infinity, clearly. So let's do 1000. That looks fine. 1000. Yeah, so it goes bad. So there's something strange about this. So these things are really, you need to be careful about numerically integrating this. Now, I'm sure that if you use the same function in MATLAB, chord is in MATLAB, it basically will do something much smarter because it's probably developed and maintained by professionals, and this is just hobbyist type software. So you need to be mindful about what answers you get, and one way to do it is to check it with multiple methods. Here you can see that Simpson's trapezoidal gives you close answers, and you also checked it with exact value. So the thing is, one thing which I see students struggling with, and this is something which we really don't teach you, is you're given a problem, you solve the problem, you go home. You don't really care if the solution is right or wrong. And one way to check the solution is right is you write a code and validate it on something whose answer you know. Like, for example, here we knew the answer is pi divided by 4. So once we know that it works, then we can use it in our code. And validation is more important than anything else. You might solve a problem, but if you don't care, if you're giving the right answer, then nobody really cares. Your solution doesn't matter, right? So validating is as important as writing the code and getting something to work. So how you validate is more of an art. It's not something which you can teach. Normally, I try to do things like, is there a problem whose solution I know? Can I check it against that? Can I find special cases? Special cases would be, maybe in this case, if I did not know the integral of 1 divided by e raised to x plus e raised to minus x, I would maybe just compute the integral of e raised to 1 divided by e raised to x. I know the answer to that, and then check it, and so on. Okay, so let's go to the next question. Okay, this is a question which actually was from a homework, and I don't think I provided the code, so but we can do it today. Okay, the problem is compute, well, the goal is to compute the roots of this f of x equals 0. Okay. Now, the reason why this problem, f of x, is something which is, I would say, harder than what we started in the class is because we only looked at one-dimensional problems. We only looked at finding the roots of x squared minus 3x plus 5 or something like that, something which was a single equation. Here we have two equations. We need to find roots of both. So we need to find x1, x2 such that f of x is equal to 0. So I give you a method to do that, which is if you have Newton-Raphson method, which basically is x1 equals x0 minus f of x divided by df dx, same formula, you can actually use that for two or multi-dimensional problem by treating f as a vector. So df dx would be what? It would be the gradient. Okay, so how do we solve this? So I give you the way to do it. We just have to figure out the code. Now, what I did was, if you go back to, this belongs to roots of equations, Newton-Raphson. So first thing I do is I take this file. I would go to my folder. This is my question 2. Put it here. Okay, and then let's save this, close this, save this, close this. On this, I'm opening Newton-Raphson too. Okay, so this is a code which will solve for x squared minus 3x, the roots of that. And I think I do it using a bunch of the bisection, regular, Farsi, Newton-Raphson. I'm not interested in this and just delete them. Okay. First thing is we'll just get this code to work. I don't think I'm going to plot it, so I'll just get to this. So let's get this to work. Okay, so it's giving me a solution. 3 is a solution. So the code works. Now let's try to see how we can modify it to answer this question. These functions and use this formula. Okay, so how hard? Well, let's see if we can modify the formula for f of x. So f of x is here. I don't know if I can just copy paste. Maybe I can. Yeah, it's a mess. Okay, I need to write them myself. So let me just do that. So first equation is x1. So remember this x would have 2 arguments, x1 and x2. So I'm writing in that form, plus 3 times x2 square minus 21, and then x1 square plus 2 times x2 plus 2. Okay. And this is just returning a scalar, but I want to return a vector. So what I'm going to do is do it this way. Then replace it here. Okay, so now it's f is returning a vector. Did I forget a 21? Oh, I forgot. This is, yeah, good catch. Okay, got that. Now, df dx is also requires a gradient. Now, when you do df dx, this is basically, and I'll write it here. What we have written is f1, f2. Right? This is just f1 is this, f2 is this. Okay, so this is probably something which I have not taught in the class, or maybe I did. I don't remember. Did I teach you how to compute df dx for a vector? Okay, so the formula is df1 dx1 df1 dx2 df2 dx1 df2 dx2. Okay, this is also if you go and search for the term Jacobian, it's basically a Jacobian. That's what you want to search for. df dx1, I wrote the same thing. df1 dx1, so df1 dx1, and then here just x1 and x2, so df1 dx2, I wrote that here, and then df2 dx1, df2 dx2, so I'll put that link here. Okay, so we can actually do this here. So it's a 2 by 2 matrix. Let's compute df1 dx1. So we need to compute the derivative of this with respect to x1. So you see that the first term is the only one which will count. So it will be 3x, 3 times. What happened? I accidentally pressed extended display. Okay. So you can do this at 3x1 square, which is the derivative of this term with respect to x1. That's my row 1, column 1. Row 1, column 2 is going to be the derivative of this term with respect to x2. So you can see that this term will be 0, this term derivative will be 0. It's only this one. So 2 times x. Okay. Now we need to do df2 dx1. So this is f2. The derivative with respect to x1 is going to be 2 times x1. And then finally, derivative of this term with respect to x2. So just 2. Okay, so that takes care of this. Okay, I need no. Oh, so yeah, my bad. Yes, you're right. My bad. Yeah, so it'll be 2 because it's just the derivative of this with respect to x2. Okay, so what I don't need b here. Newton-Raphson only requires one guess. I don't need the tolerance. Oh, there's tolerance. Okay, I need tolerance and iteration. So now I'm basically, well, there's one problem with the A. You know what the problem is? This is the initial guess. Is this sufficient? What do I need? What are the variables here? There are 2 variables, right? X1 and x2. So I need to supply it with 2 variables, 2 inputs, say 0 and 0. Because there are dividing roots of 2, it's function of two values. Okay, and so we pass it here. Now, if you look at Newton-Raphson, this is made for only one dimensional. So you need to df, dx. It's just doing df. Well, this is just taking the value from there, so it shouldn't have a problem. This shouldn't have a problem. It's this part which will have a problem because by the formula, I need to put df dx inverse. So the inverse is not specified yet, just this. This will work for a scalar, but will not work for a vector. So I could do this. Let me keep this commented. So I could do inverse EFX. And what happened with the wrong file? Okay, I have it here. Okay. So this, what I have here, this thing here is exactly what I wanted here. I think I should be good. So now let me run this. Okay, there's a problem. A must be a square matrix. Okay, line 20, column 8. Okay, I thought that it was square, right? DF is, oh, I see the problem. Right, I wrote a 4 rows. Oh, sorry, four rows instead of 2 by 2. It should work fine. Let's try this. Okay, so here's a problem. We have saying that not a number. Matrix singular to machine precision called from Newton-Raphson, line 20. So it's saying that this is a problem because it becomes singular, it becomes infinity. I think it's to do with the guess. So if you see this 0, 0, if you put initial guess of 0, 0, 0, the determinant of df is going to be 0, right? It would be 0, 0, 0, 2. When you put x1 equal to x2 equals 0. So it will not work. So there's a problem with Newton-Raphson is if this is singular, if the inverse is not defined, this will never work. So there are ways to fix it, but the easiest way to, there are methods where it can take care of such a input. But the easiest way for us to fix it is to not try 0, 0. Let's try 1, 1. Okay, there it is. Now he gave us a solution. Okay, do we know if this is right or wrong? We can check this quickly. It actually printed it twice, and that's actually a flaw here. Because I said root has 2 values, so you could actually fix this in this fashion. Root 2, and then put and percentage 4f is sufficient actually. 4f. Now, here it is 1.68 and 2. It's printed slightly differently. Okay, now we need to check if this answers, these values we got, actually satisfy make f of x go to 0. So how we'll check it? Well, just do this. Just f root, right? Root is the two values. If I put them in here, they should give me 0. So we can check that. Okay, here it is. So it's saying that it's 1e negative 1, 1e negative 4. It's not very accurate here. This should be 0. It should be like 1e negative 6. Now, seems like there's a problem. The tolerance here was specified to be 1e negative 3, but one of the solution was only accurate to 1e negative 1. So we have a problem. So it's to do with this, the way we compute this. Okay. We need to check individually each value. Okay, so how will we fix this? Can you suggest of a way in which we can check? Well, we could do it this way, but it'll become very specific to this problem. We could take well equals this. So this is basically computing the absolute value of f of x. Well, let me do it this way. F of x2 is f of x2. So this is going to give me a 2 cross 1 vector. I can check each of them. So abs f1 is abs fx2 1. So I'm taking the absolute value, the first of those rows, and then abs f2 equals abs. And then maybe what I need to do is I need to check abs f1 this and abs f2 need this and need this. So now it's going to check both of them to be true, right? So instead of checking earlier I was not doing that. I was trying to square them and sum them. So with this, maybe it will work better. Yes, well, didn't work better. So it gave me the same answer. Or maybe I didn't run it again. Okay, so there's a problem. We were not successful. See what's going on here. This condition is flawed probably. It got out of this condition without it got out of this condition. Shouldn't have got out of this unless it checked both of them, but one of them is not true. Okay, so how can I fix this? Maybe I can just print this and see what's going on. So it's just printed several times. Okay. So when this happens, I should see, it should basically check this is less than, so this is less. I see what the problem is. So here the absolute value actually took the negative. Oh no, it's a positive value. 0.4 is 0.4 less than. This is not true. And this is true. This is true. This is not true. So not true and true will become not true. So this OR is a problem. So this with OR this, I think doesn't work very well. So what we'll do is let's get rid of this. We just check based on the absolute value instead of using the tolerance between two values. Okay, that did not help, looks like. Let's do this. Okay. Okay, that did not help. So how can I fix it? It should still do some iterations. Shouldn't leave it like this. Any ideas? So I don't understand this. This one is less than tall. Tall is 1 in -3. So this value is less than tall is not true. And this value is true. So I don't understand why it's terminating here. Let's check if it's actually terminating here. So I'm just going to unprint this. Interesting. So it actually did not print this. So it's not terminating here, it's terminating somewhere else. Is it the iterations? No. Error is, okay, what is error? Oh, here it is. That's where the problem is. So it terminated based on this. It never really get caught here. We could just add the two, which will make it a lot worse. Okay, in maximum iterations leap, we have a different problem now. So let's go and fix the iterations. Let's increase them. So we have 100. Let's make it 1,000. Okay, so it's better now. So here we have the f root is 1 in -4 in -9. And this is the solution. And so we are all happy. So we got it. So I mean, this is what entails in getting something to work. You just have to make sense of errors and what you expect, what you don't expect, and fix it. So this code which I have here is not foolproof. It's not going to work for 3 or 4 variables because see what I did here. I basically this is only tailored for 2 dimensions. Okay, so clearly, if you want to write it for n dimensions, then this needs more work, but sort of I can hopefully tell you that this is on the path of getting to the point where you can write code for n dimensions. So we are